Yeah, it was so much fun. And then she came back to my room and we did some snacks together. We're just hanging out. Honestly, I don't have one. Like, nothing pressing. What did you
But like this is the first part, right? The stuff that we did in class.
I think there were no people. I don't know what you said.
All right, cool. Welcome back. Thanks for joining, getting here through the icy mess that is Northeast Connecticut after some snow, a lot of ice. Like somehow we just ended up with more ice than we had before. But in the last section, we were working on homework 1. Not to say that we can't finish today, but we didn't finish this morning. So I pushed it off until Tuesday, so we have another day to take a look at it and then submit it on Tuesday. Any issues? Like if you're done, then it's like sweet. You can submit and be done with it. But if you want to take a look at it like on the same schedule that we're doing, then we'll keep thinking about it, kind of discussing approaches that way. Sound good? That's the first kind of logistic thing. And then right now we're on to this like last part of homework 1. Were there any like lingering questions or things from the first few textbook problems that we were working on? Now that you've had some time to like really go back home and talk to your roommates of like, hey man, you know what we talked about today was like the effect of mass on skiers and what their terminal velocities are. And your roommates are like, dude, leave it in school. Get out of here. Going once, twice. Move on. Keep charging ahead. All right, I'm up for that. You can always grab me as I walk around. Like if you do have questions, you can always stop and ask those. So our goal here is find x of t. Where do we start? Like that's like there's going to be a lot of steps to get there. What's the very first step that we should take? Which one? Free body diagram? Free body diagram? Sounds good. Yeah, if nothing else, this class should be an immediate response of, oh, you're talking about motion? Where's your free body diagram? Like that should be like the two things. Because even, like I've talked to people that work at like Otis, like building elevators and like all kinds of control systems. The very first thing that they do to like onboard new engineers is draw a free body diagram. Like it's just, that is the standard practice. Like if you're trying to move something, you need a free body diagram. If you're trying to make sure something doesn't move, you still need a free body diagram. Like somehow you got to know what's connected, why are things moving, what's causing it. All right, so we need 3 free body diagrams because we have 3 different scenarios. What do they look like? Here's A, there's B, there's C. I'm already drawing it as a point mass. If you don't want to draw it as a point mass, that's okay, but I think it's okay to draw it as point mass. X is like the actual position. So like if X is 2, it's 2 meters away from where it started. In this case, we'll have like an initial speed, but the free body diagram should be something that is the same whether it's moving or it's standing still. Yeah, that is good. Good, right?
So you have force and then force friction first.
Okay, yep. viscous damper. Yeah. But you're not the only one. I can guarantee half the class does or doesn't know. What the heck is that? What is this thing? As it catches up slowly. What is this? A damper? Yeah. Nice. Sweet. What does a damper do? Have you ever like used something that has a damper? Yeah.
Like absorb the motion.
Absorbs motion. Yeah. So it's specifically an engineering thing to like get rid of speed, like slow things down. Why would you want that? Yeah. So they don't move too fast. Yeah. Yep.
Absorb vibrations.
Absorb vibrations. Yeah. That's another good way. Have you ever been in a car where the shocks are blown out?
Yes.
It's like nauseating because when you hit a speed bump, you'll bounce up and down for the next 2 miles with no damper. If there's no damper in there, you're just all you have is springs, and for springs, at least like that simple harmonic oscillator, it's gonna harmonic oscillate. It's gonna keep bouncing up and down until something slowly slows it down. So even like this door that you just walked in this morning has a little torsion spring and then a torsion damper. So the faster the door moves, the more force it applies to slow it down. So this is a linear damper. Oh, not a tinier damper, a linear damper where the force is some constant times the speed. So the faster you move, the more force it applies. And it's a nice way of like taking kinetic energy out of the system without storing it up in like a spring or something. It just like dissipates it. Main way that we use it as engineers is like and I think I don't have it. So let's look it up. Viscous damper. Images. Yeah, something like this. I am a human. Something like this, where you have a piston, but the piston isn't trying to like move the fluid, it's just trying to move through the fluid. So the more orifice, like the bigger area you have for the fluid to flow through, the less effective it is. The less area you have, the harder it is to push that. So the more damping you get. Like in terms of like, I want to put a damper somewhere, like in my shoes. That's what you would need, like some kind of liquid pushing through an interface. And now you have these like slowly sinking shoes every time you step. It would be kind of annoying, but you could do it. You're engineers. That was a big long explanation to say F equals B times V, but that's what it is. We have like, the faster we go, the bigger the force. We can say like smooth surface for those. If you want to add friction, you can, but it'll be easier to say like, but mu is basically 0, so some kind of smooth surface.
It's pretty much like the same for all three.
They look all the same. Okay.
The force is weird.
Okay. Okay. Oh, and you're having like FA. What is that one?
I'll apply it first.
And apply? What is that?
Just
Is
like the
it
initial force equals the
so something? Okay. So far I've seen these forces, like all 3 cases, it's not going to go through the floor, so there needs to be some kind of reaction force, and then there's still weight acting on it. And so far I've seen like Like force of friction pointing that way, or like mu times n. Is that force of friction opposing the motion? Which way is that B times V damper force acting?
Against motion.
Against motion? Okay, so which way would we point that? To the left? What if it was moving to the left? Would we need a different free body diagram than to the right? What do we think? Yeah? So we need two. So this one we would have to split up into two different ones. Depending on if we're moving forward or backward.
But it need to split the first one too.
Would we need the first one to be split too? If we're moving backwards, so yeah, I don't know how to pose it as a question, so I'll pose it as a statement. When we're moving backwards, v is a negative number, right? Like the change in x over time is a negative thing. So what I can do instead of saying that there's two cases, forward and backward motion, I can think about like only the forward motion, so that when it's moving backwards, or if it moves backwards, it's still the same force, but it's a negative BV. So it's a negative of a negative, now it's a positive force. Kind of makes sense? So we don't need, at least for linear dampers and for linear, which is the next things, when we have this linear stuff where it's V, we don't need two forces for different cases, which kind of spoils the next part, part C. Which way should our spring force go? Yeah.
Wouldn't that sort of depend on how compressed or stretched the spring is?
Okay. So does it depend? So initially we're going to say that it's totally unstretched. No compression, no stretching. Should we draw no spring force?
I would draw a spring force because doesn't like that X show a displacement of the object, or am I misinterpreting?
So what we're doing, what the diagram is showing us is like when X is positive, it's going to move that way. Yeah.
So then,
and there is going to be positive X motion
so
in this case.
There should be a spring force.
So there should be
to the right.
To the right? Like this way? Sorry, it'll catch up in a second. So pointing that way, spring force?
Yeah, this. Yeah.
Yeah. So as I move forward, the spring is going to keep pushing me forward. So the farther away, so if we think about it like I attach a spring, like bungee cord to myself to here. If I move 1 meter this way, now I have K times 1 meter pushing me that way. Now I have K times 2 meters pushing me even faster. Yeah.
It's pulling it back as you're going that way until like you stop and then it might pull you back.
Pull back. Yeah. So maybe this way. So if we, and this is the way that I like to think about it when I'm like building a free body diagram, because sometimes it's not as straightforward. Sometimes springs are sort of like attached to angles and weird things. I stop and think about like, if I increase this value, like if X increases, where is that force pointing? So for a positive X, it's pointing in the negative X direction that way. It would be nice, it would actually be incredible if it was the opposite. If the further I went, the faster it pushed me, because now you have like infinite energy, right? Because all you have to do is give it a slight push, and now it'll accelerate to like speed of light within like a few, I don't know, depends on what the exponential constant is, but it'll go really fast, really quick. It'd be nice. So if you do find a spring that pushes, the further you go, the more it pushes you, great, yeah, go for it, use it. But here, what we're kind of seeing is that all three of these are called restoring forces, like things that are bringing you back to zero, something that's like spring pulling you back to zero. Now you have a lot of kinetic energy, so it sends you through zero. Anyway, all this cool stuff. So all three of these are equal to a kinetic diagram. So it's the same kinetic diagram because it's all three of them have the same like geometry of motion. They're both moving left and right. So what does the kinetic diagram look like? What does that look like? Sorry, I didn't put your FA on there.
Okay.
And like, so you can think of it as like some force as a function of time. Like that's a general kind of like vibrations analysis. But in this case, like we know the initial position and initial velocity. That tells us like how to integrate the equation. When we integrate twice, we have two constants to solve
So
for.
we don't need to show the force.
Yeah, yeah. Because we're just trying to capture like what are the things happening after time zero, and the FA is applied at time zero. Yeah. But you can leave it if you want. It's just like only at
it would be zero.
Yeah, it's zero for the rest of time. Okay. Yeah. Kinetic diagram, it should describe like just what is acceleration, independent of like what forces are applied. Because we're saying like F equals ma, so we should have some definition of A. If we see the thing moving to the right, say, all right, that's A. Accelerating to the right. So that's what we're trying to do here. But you're right, like it's a function of those applied forces. That's like the next step when we say F equals ma and then solve for A equals something. Oh, okay. So does it change? Like in the case of the spring, it's a at least a good practice.
Actually working on a project.
Okay. Which one?
A damper dyno.
Oh, nice.
Building a damper dyno. Once as you're going to measure.
Why do you want a damper in your dyno, like dynamometer?
No, you're building a dyno so we can measure if measurements for damper. Because we put it in our car.
Yeah.
So you don't have any measurements, you just eyeball it right now.
Yeah.
We're working on building this one.
Awesome.
My blanket here.
Alright.
I was my entire
So what I've seen so far is a lot of people are kind of like already thinking of like what is the solution for MA? Like MA is pointing to the left. But we were just talking about like positive and negative kind of values. The best practice for kinetic diagram is just if you're saying that my x-axis, so as a group we're all saying like x this way is positive. So that means in my kinetic diagram I want to say A that way is positive A. So we just want to say in the kinetic diagram that MA is describing a positive acceleration. And that might be like a little bit weird. And I guess the main weird part there is like in statics, a lot of times it didn't matter. Like if I say the reaction force is up and I get a negative, then it's just the opposite of what I thought, and it's not a big deal. Here, because we have like things moving and we're trying to describe motion, we want to make sure that our vectors are aligned the way that we're describing. So a positive, when we say positive MA, we're saying it's going that way to the right. Yeah, right. Stage left. Wait, stage right? Yeah, stage right. That's the one. It means left. But anyway, long explanation, but MA, so the nice part about that is like kinetic diagram, you don't even have to look at your free body diagram. All it's describing is what are your axes, like where is motion happening and where can acceleration happen. So in this case, it's only moving left and right, so we only need to draw an arrow to the right. Otherwise, we would have like a positive MA equals a positive BV, so we end up with that same problem that the faster we move, the more acceleration we get. More velocity, more acceleration. So now we're going to come up with 3 different values of acceleration. So I wrote it out in all 3 forms at the top, like a d squared x dt squared and x double dot. They're all saying the same thing, at least in this case, because a is just x double dot, and then just the x double dot in the next 2. So what are these parts? Yeah. Yeah, and that's okay. So we're saying MA equals negative K.
So you're just saying what's going on with negative?
Yeah.
Okay. Okay. That's just like a frame of reference.
Yeah. And that way, my equation that I'm going to solve, like the differential equation, is MA equals negative K. It's not MA equals KX. Yeah. Okay. Yeah. 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 No, it's not a force. It's just saying it's work. Yeah. Yeah. So like when I go back, like X, it goes from starts at 0 and goes whatever 3 meters at 3 seconds. That clock started at 0 and then went to 3. No, no, no. Can you use a kinematic equation when
Well, because I'm doing some of the forces and then solving for A.
Yeah. But this one assumes A is constant, right? But here A is a function of velocity.
Yeah.
Yeah. And velocity is a function of time, so A is a function of time.
Right, yeah, so it doesn't work.
Yeah. Yeah, so we can't use these equations. We have to go back to this one and say that dv dt equals negative v over n times v. And then we can like put v on one side, t's on the other. Integrate both sides. Oh yeah. Oh, we're going deep. Yeah. Same. Okay. Same issue. All right, so I saw some people kind of getting into it, but we have a negative mu ng. So in this first equation, equation A, is mu ng changing? Like, are any of those a function of time or position or velocity? Mu should be like some constant coefficient, right? M also some kind of constant mass. We're not accounting for like the mass loss due to slide. Like it's not an eraser that's losing mass along the way. And then G, definitely constant. Technically there's like Yotvos effect and Coriolis effect, but we're going to ignore all those because it's only like, that's like the 5th or 6th sig fig in the 9.81 value. So in this case, we know A is constant. When A is constant, that means that we can use those kinematic equations because they're already integrated for us. At least if that's already been like, if you have a tattoo of the kinematic equations to get through freshman physics or like high school physics, you can use those over and over. Then I saw this one, like negative BV, like that. Good so far. How about, oh, it's catching up. I feel like it's really slow today, right? Let's get there. Negative BV. Is this one changing? Is this a constant acceleration? Can we still use kinematic equations? B is constant. What about V? Is V constant? V is our speed, right? Like that's how fast we're moving. So acceleration is a function of speed, but speed is a function of time. So here, A is not constant. Yeah.
So it's decelerating.
In this case, it's decelerating. Yeah. Yep. And I think for the most part, dampers are always going to like take away speed. Yeah, I'm trying to think. I don't think there's any cases where a damper would like speed things up. I'm pretty sure for the most part, it's always reducing, like getting rid of, because you're taking your kinetic energy and converting it into fluid motion, and the fluid motion just kind of dissipates as like heat and stuff that can't use. All right, so A is not constant anymore. So we gotta solve for our own kinematic equations there, because kinematic equations are really like a differential equation that's solved for a specific case of a equals a is a constant. Last one, any issues here with like negative kx? That's what I saw so far. Looking good. And so, yeah, kind of walking around, people with MA pointing the other way, really what we're trying to get to are these like, differential equations when we have a free body diagram and kinetic diagram for dynamics. If things are moving, then you want differential equations. Whether or not you want differential equations in your life is a different question, but at least in this case, it's good that you ended up with like a second order differential equation. That means things are going well because you've identified variables that are a function of time and time derivatives. We're good. We're on the right track. So I think A we can come back to A, but we know kind of how. So let's go into part B first. And I'm going to solve for A. Like this. A is negative B over M times V. What do I do with that information? X isn't even in here. Like, how am I supposed to get to X of T from here? Any ideas? Yeah. Integrate? Yep. Okay. So can I say integral of A dt equals integral negative B over M V dt? Like this? How does that look?
B and M constants?
B and M, sorry, B?
Yeah, like B is like a given constant.
B is a constant, yep.
And M is just an S.
M is a constant, yeah, so those are good. And then what about V? How do I take integral V dt?
dt.
V times T? But V is a function of T.
So then that would be like V squared over 2.
If
Well, you said it's V of T, right?
V of T, yeah.
It'd just be X of T, right?
Is it X of T?
Oh yeah,
Is the derivative.
yeah.
Okay, so then we need to take an integral of A to figure out X of T is integral of A?
Well, integral A would just be V of T, right?
Now it's V. So then we end up with the same. Now we're rederiving A equals dV dt, which equals d squared. So something's weird, right? I put us into a corner on purpose just to see where we'd end up. So let's backtrack a little bit, and we'll dust off. We're going deep into some calculus knowledge that you had tried hard to like forget. So instead, we'll say dV dt is A, right? So A is change in velocity. Does this look familiar? Damn, calculus, always sneaking up on me again. So with like these, with the dVs and dTs, they're all just variables. It just means like a small change in V. You can play around with them and you can move them around same way as you would with like fractions. I can't say that dV times V is like V squared, but I can move it around. So that now I can say integral of both sides and I get a function, I'll have like v of t, right? If I integrate the left-hand side, 1 over v dv, and the right-hand side. This is something that I like to do in general. Some people don't mind adding extra constants, like doing indefinite integrals. I like my integrals to be definite. I want some structure in my life, at least little parts of my life. I make exact integrals of going from v0 to v of t and from 0 to t, and that way I don't have to deal with that, like, don't forget to add a constant when you do the indefinite integrals, because the constant subtracts out, it just disappears. So give that a shot. See if you can get through calculus question from, I don't know, 3 years ago, 4 years ago? Depends on when you were working on it. Oh, you're setting it up as like ODEs? Oh, nice. Yeah, yeah. Yeah, you got the right hand side. The left one, so integral of 1 over x is log of x, like natural log of x.
Oh, you're oh yeah, I forgot. Yeah, I just use it. Yeah, so it's like in terms of like a differential equation, it's just I would multiply both sides by like I mean maybe C does that.
Yeah, so like I don't know log of v is yeah.
So then
And whenever you have
oh yeah, no, I
log
forgot.
of v
Yeah.
minus log of v zero, log of v. Yeah, and that makes it a little.
Well, you don't use anything. You put it to base to cancel out the log. But like how you do that is you combine these two, where it's like L has this over that.
Doing some, oh yeah, this is really testing your trivia knowledge on logarithms and
That's
calc.
not the issue, yeah. It's
Yeah.
just, yeah.
So we end up with like log of v, so like v of t, like at least our first step to get to x of t. Log of v minus v0, log of v0. But I can combine those of like v of t over v0. And then take both like e to the something, so v of t, e to the negative b over m. Oh, it would help if I didn't just delete my v0. So now I've got like v0 e to the negative b over m times t, something like that. Cool. And then we can do it again, because we're getting good at this. And it's just fun taking integrals. It's fun. So integral, so dx dt. How do I get the integral here? What do I do? What's the first step?
Integrate both sides.
Just integrate both sides? Like this? Can I do that?
Oh wait, no.
Yeah, something. But yeah, like we want to integrate both sides.
You want to multiply both sides by dt.
Yeah, so let's get rid of that dt. Put it over here so that the right hand side is like something times dt is our function. So now right hand side, all a function of time. Left hand side, all a function of x. Integral dx. We know how to do that one. At least we did. At one point we did. Now we're relearning it. And again, I like to start at x0, go to x of t, like make exact integrals for everything, and then start at time 0, go to some time t. I'll give it a shot. You give it a shot. Oh, I didn't actually do anything, did I? How's that? I always have trouble with integrals. I don't know if anybody else feels that, like the same way. Derivatives I got, like I can always take a derivative, but integrals I always have trouble with. So the Richard Feynman approach is never take an integral, just always do derivatives and just try to guess what derivative you need to solve the integral. So in this case, I know d dt e to the negative b over m t is negative b over m e to the negative b over m t. So that one it's like, I remember that all the time because that one's a little easier for me to remember, but it's harder to remember that the integral is 1 over that constant. So I can solve for, do the same thing that we just did, right? So I can solve for integral of that function. And to do that, I just put a negative b over m over here. Or sorry, I got to multiply by the m over b. Kind of nice. So now like integral of e to the negative b over m dt, which is what I was trying to find. What is the integral of that e to the negative b over m? It's m over b, the negative m over b times that. Kind of a nice way of doing integrals without having to remember what the integral is. Okay, anyway. So we have negative m v0 over b e to the negative b over m times t. Is that it? Yeah.
Wait, why is it negative m over b instead of negative b over m?
When you take integral?
No, like, because I'm supposed to be, so if I'm taking the derivative of e to negative bm over t, it's e to the negative bm over t times the derivative of the inside, which is negative b over m.
So here,
Unless
star 1, star 2. So you mean in the first star or the second star? Like the top or the
first
bottom?
Star, I guess. Well, I mean,
Okay.
I guess like, well, where you have like the bounds from like t to, or your antiderivative basically of the
Yeah.
right hand side. I'm saying like isn't it supposed to be b over m instead of m over b?
So integral of b over m times t is the 1 over.
Is t on the denominator? Wait.
Oh, it's b over m times t.
Yeah.
Like bt over m.
Yeah. So then
Okay.
the derivative of that is negative b over m.
That would be derivative, but we need integral because we're going from v to x.
Oh yeah. Wait. No. You're
Yeah.
right. You're right.
That's why I
I'm
always,
like,
I usually have to do
yeah,
this step and like convince myself like, is
for
it?
some reason my mistake.
Yeah. I mean, we definitely, like, they're all connected, derivatives and integrals, but it's pretty easy to get confused. But for some reason, derivatives feel easy, but integrals always feel like harder, even though they're just like fancy summations. That's what my partial differential equation instructor told me. We like did all this math, and then the final solution was an infinite sum of infinite integrals. And he's like, and that part's easy because it's just a fancy summation. I'm like, what? Like, how is that the easy part? Like having all these integrals all summed up together. Anyway. All right, so this last part, is that all we need? E to the negative b over mt? Yep. Yeah, minus 1, because e to the 0 is 1. So subtract that 1 term here.
So did you like guess the integral? Just like off of like tuition, like intuition and like what you thought it would use?
Oh, going from that top one, from star 1 to the next line. That one, I knew the integral, but it's because I've done this a dozen times where I take the derivative and then solve for the integral backwards. And at one point when I was an undergraduate, I just knew it. Like I knew those integrals because I memorized all that stuff. And I'm sure you're going through that stage now of like what needs to be like concrete memory versus what can you dump. Now, this is the hardest part about dynamics, is pulling everything together. And I think I said that already, but we're going to keep doing a lot of that where it's like calculus, geometry, trig, physics, like everything is all coming into one place. Cool. Have a great weekend.